You mean the video is going to be available on YouTube too, or it is just to show in live?
Up to you, but we prefer that if you could leave it on YouTube also for
Yeah.
watch
You can leave it. You can leave it for sure.
Because we found that it's appreciated for people are watching afterwards.
Yeah, I understand. Yes.
So it's 11 and it's time to start our today's webinar in this Lignin online series. This is a series that we make together with, we have a webinar series that we arranged together with Wallenberg Wood Science Center. And the Lignin online series ends with a workshop that is arranged by Lund University. So please check out our website to find the times and to register for the workshop. So we're welcoming you both who are attending us here in this Zoom webinar and you who are following us on YouTube. And of course, we especially welcomes today's speaker. It's Professor Xavier Crispin from Linköping University and the Laboratory of Organic Electronics. So, and Xavier, you're also a part of Wallenberg Wood Science Center.
Yes, indeed, yes.
So, Professor Xavier's research is focused on the use of conducting polymers as energy materials in supercapacitors, thermoelectrics, and fuel cells. And today, the title of the talk is Lignin for Electrochemical Energy Storage. There will be possibilities to ask questions to the speaker after a Q&A session will be held after the presentation. So you in Zoom, please use the Q&A function, and you at YouTube, please use the live chat function. So with that, I will leave the word to today's speaker.
Okay, so let me share my screen. That should be it, this one. Do you see properly?
Yes, so please put it in presentation mode. Now we see it good, but in PowerPoint.
Do you see the presentation mode now?
No.
No. Maybe I share the screen. Let me try again. It's like this, it's okay.
If we see it in the PowerPoint. See it in PowerPoint mode currently, so. So to say, we also have in the webinar, we also have Professor Martin Lavoko from Wallenberg Wood Science Center, who will help us with the Q&A. So we seem to have technical problems. We just so we lost the speaker so we hope that he will connect in a minute or so. Again, there seems to be some problem with the connection. So please stay tuned and we will be back as soon as possible. In the meantime, I take the opportunity to also announce next speaker that we usually announce in the end of the webinar, but now that we have some time here while waiting for Xavier, we have next presenter now on Thursday, and it's Martin Lavocco, who are following this webinar series has met in the Q&A session. Now he will give the talk on lignin heterogeneity effects on lignin valorization, and that will take part on Thursday. So I guess we have to put some pause. We should have had some pause music, but we will try to connect with Xavier as soon as possible. So stay tuned. And now we're back. So
I'm sorry, a computer crashed. I don't know why, but this happens.
Welcome back.
Yeah, we're very happy to have you back. And so now I leave the word to today's speaker,
Yes.
Professor Xavier.
Okay, I try now again. I hope it's going to work now.
It still seems to be your computer does not. Now we see it now we see it perfectly.
Okay, great. Thank you. Sorry for the inconvenience here. So I'm going to tell you about how to use lignin in electrochemical storage. So electrochemical energy device, there are different types of it. And all of them are somehow built on the same kind of architecture. That is to say, electrodes that conduct electrons and ions, and an electrolyte that conduct ions. So there are different types of devices, electrochemical device, from capacitor, supercapacitor, batteries, and fuel cell. We are going to focus mostly on batteries. So you can divide and those different type of device as categories on a Ragon plot. The Ragon plot is a plot of the specific power, so which is the amount of energy per time that you can provide with the material for a certain amount of mass. So this is a specific power in watts per kilograms. And then you have the specific energy is the amount of energy per kilogram that you can hold in a material. So you can see that there are devices that are very powerful. You can deliver a lot of, quickly the energy, like capacitor, supercapacitor, and there are devices like fuel cell that are slow, but you can have a large amount of energy. And somehow, for batteries, you see that starting from the lead acid battery, which is still the most widespread battery, this has decent specific energy, not very high power. And with the, new batteries have been striving to increase both the energy and the power. So you see that nickel cadmium, lithium ion batteries, you get higher and higher in energy and in power, basically. And the big question that we have as a scientist and chemist is that can you do something with organic materials, and how good can you reach in this kind of Ragon plot, basically. So we'll classify two types of energy storage device, what I call solid state, and then we'll look at liquid state also. So for the solid state, we will come back with a little bit to the basics in electricity, speaking about capacitor and introducing the concept of capacitance. So a capacitor here is a two-plate capacitor based on two electrodes sandwiching a dielectric material. And when you apply a voltage to those two electrodes, you can have a certain amount of charge on the plate. And the certain amount of charge on the plate divided by the voltage you apply is defining the capacitance here of your capacitor. So this is also related to the type of material that you have inside. So if you have a material of a certain dielectric constant epsilon, and the area of the plate electrodes is A, the distance between the two electrodes is the small d, then you have defined a capacitance based on this geometrical feature as well as the material that you have as the dielectric. So you can store then a certain amount of energy E, which is basically proportional to the capacitance 2V squared. So you have other type of a capacitor where you, instead of using a classical dielectric, an insulator, you use an electrolyte, so salt in a solvent basically. And then when you apply a voltage to the two electrodes, what is happening is that spontaneously the ion of opposite charge are going to form a layer in that way by spontaneously reorganizing the position of the ion in the solid right at the interface, basically. So the difference here is that the different distance between the plate of charge is extremely small. We are speaking in terms of angstrom here. So so it means that if the distance is very small between the plate of charge, if you look at the equation of capacitance, then the capacitance will become much larger, basically. And that's why, I mean, in those electric double layer capacitor, you can store much more charge than in a conventional capacitor with a dielectric. So typically, you can say that the dielectric capacitor, they have a small capacitance, but they react very fast because it's another kind of polarization. It's like electric and dipolar polarization. You are reacting faster than nanosecond. And in the electric double layer, you are reacting in the order of microsecond, and you can get, so they are slower, but you can get a lot of more energy stored on those plates. So this is just for plain. Now, if you want to go to supercapacitor, the first supercapacitor you would do is that you would have a solid that is conductor and have a large surface area and have an electric double layer on a large surface area. This is the way to get a higher value of charge stored. And this is the first phenomena that is sketched here as a figure A. Is basically an electric double layer, but with a porous, with a nanoporous solid that is conducting. So typically carbons are used very much for that, conducting carbons. Now, there are different types of electrode process when you go from supercapacitor to batteries, and they depend very much on the phenomena that is occurring during the charging process at the electrodes. So we mentioned about this electric double layer form for the supercapacitor, but then you have on the other extreme at an even smaller length scale, you have the phenomena of batteries where you have basically, it can be, for instance, for lithium-ion batteries, the insertion of an ion like a lithium inside the material. Now we are not talking about a few tens nanometer, but we are talking about a few angstrom between layers of material. So we are really intercalating ions into the solid at a very tiny scale. So in that case, it becomes more like a battery type of behavior where you have like an electrochemical reaction of the solid itself, because you're really coming at the fundamental small dimension of the solid. So we can then distinguish what is called non-Faradic process, where you don't have really an electron transfer to the material. and Faraday process in which the material itself, so this is going to undergo a redox reaction. So if you have a redox reaction, it typically occurs at very specific potential. So you will see in the electrical characteristic plateau or feature or at a certain potential, while in the electric double layer you don't have any specific feature. You're just charging a conductor more or less by this electric double layer. It does not depend on the potential. I mean, the more you put potential, the larger charge you put, but there is no specific threshold or any kind, because there is no redox reaction, there is no electrochemistry going on. So we can look, this then will appears, this kind of behavior, different behavior will appear then in the electrical characteristic. So if you look at a cyclic voltammogram, which is basically you scan the potential, you measure the current and you scan the potential in a constant fashion. So you have a certain scan rate, and then you increase basically the potential step by step. You increase, and then you just follow and measure the current. So what you have in an ideal capacitor, in even electric double layer, is that the current is then directly proportional to the scan rate, which is constant in the experiment, times the capacitance. So the value of the current is directly connected to the capacitance value for a certain scan rate. So here you see you obtain this level of current, the red, is connected to the capacitance. Now, after, if you scan back and you reverse the scan, you will have a dV by dt is going to be negative, and then suddenly the current is going to be negative also. Then you have a square box. It looks like a square box. When you have a square box in a cyclic voltammogram, you know that you have a capacitive behavior, basically. So in terms of charge discharge, you can also do another experiment. It is to apply a certain current which is constant on between your two electrodes. So you keep a constant current, and you see how the voltage is changing. So you can increase the voltage when you charge, and you can see how the voltage decrease, how the potential decrease when you discharge. And this is such a curve here. The potential decrease in that case linearly with the time. This is a feature of a capacitor behavior. So supercapacitor, they have a linear behavior. As I told you, there is no specific threshold like electrochemical behavior. On the contrary, if you go below in the last, on the bottom here, there you have a specific feature of an electrochemical reaction going on in the solid. So you see specific peaks appearing in the cyclic voltammogram. You have this peak sporadic, so you have an electron transfer reaction inside the solid. And then at those potential, then you will have a very specific threshold, basically. So you have a constant potential versus time, and then until all the redox reaction is happening. Then after, when the redox reaction as occurs in the solid, there is nothing more to be done. Then the potential suddenly drop, basically. And this is the ideal feature for a battery. You want to keep the voltage constant as long as possible. Then your battery is discharged, and you need to recharge it, basically. So this is the difference between supercapacitor, where you have a discharge where the potential discharge with time, and then a battery where you will have a rather constant discharge. And then you have all in betweens. So many nanomaterials show behavior actually in between those two extremes, where you have both a capacitive contribution and also a Faraday contribution. So it is not as extreme as those two ideal cases. And this is what we are going to show today, is that you can have also a capacitive behavior and a Faraday behavior depending on the composition of your electrode with lignin. So speaking about organic energy materials, I'm going to introduce a few families that we are going to discuss about. So first of all is the lignin that you know very much about, I mean, that you can find abundantly on the market. as lignosulfonate, alkali lignins, and other kinds of lignin, basically. So lignin is an amazing material because it's one of the few biopolymer that is aromatics. And the fact that it's aromatics introduce very interesting feature because it's basically redox active. Some of the groups like are quinones, and those quinones or hydroquinones, they can basically undergo a redox reaction. So in that case, you see the hydroquinone here can lose the two protons basically when we have two electrons that are involved in the reaction to get the quinone. So this is nice. You can do redox reaction probably with a kind of in a chemical way, but it is not very useful because at the moment, if you want to use that material as energy storage in a battery, what you would need to do is actually to find some kind of wires at the molecular level to bring electrons in those quinone sites, because lignin is an electrical insulator. So you cannot just put lignin on an electrode and get a battery material. It does not work like this because it's an insulator. So on the contrary, you need to try to find a strategy to bring basically electrical wires as small as possible. So molecular wires at the scale of these molecule, so that you can bring electron in each side of the lignin. Then you will basically be able to use lignin as a charge storage material. And this is what we are trying to do. So I'm going to introduce you small nanoconductors. The first category can be conducting polymers. And this is from basically a discovery in the 70s, from which has been awarded the Nobel Prize in Chemistry in the year 2000, is that basically conjugated polymers, so polymers that in their polymer chain as an alternation between double, single bond, those kind of conjugated polymer can be doped by oxidation and become then conducting. So they are like a little bit like you have semiconductors and you dope the semiconductor to get it conducting. So it's the same here. Upon oxidation, you kind of have a doping and you introduce charge in the polymer chain. And those charge are carried by the pi electron system, and they are going to basically be responsible for the charge of electronic of electrons, of current through those. So they are going to be molecular wires, basically. Their conductivity can be actually quite decent, like bad metals. But these are interesting materials because they are processable from solution, and they are flexible, and you get these molecular wires. So those could be nice to introduce with the lignin, basically. So another type of conductor, nanocarbons, are all these abundant families of carbons, like fullerene, single wall carbon nanotube, multi-wall, graphene, nanodiamonds, as well as the feature or the kind of carbons that are larger, like mesoscopic scale, like in carbon nanofibers, carbon blacks, nanographite that we are talking a lot today. So those are larger size entities that could be also very used. Carbon black, activated carbon, are very much used in battery technology because they're super cheap and they're quite small. So you see carbon black, it's something like 100 nanometers in diameter. And it's composed of amorphous part and as well as graphitic parts. All right. So one of the things that people have been doing is actually use lignin as electrode material by carbonization. So basically, it is to heat at in nitrogen to heat at almost close to 1,000 degrees lignin and form basically aromatic rings, and you form step by step that start to conduct electricity because it's aromatic. So you have like graphene sheets and graphitic planes that are formed. There's also the potential to use the fact that the lignin is very amorphous, to introduce porosity and nanoporosity. So you can, for instance, obtain by different treatment carbon material from lignin that have a surface area of 1,500 square meter per gram. So it's a very large surface area. And then you can basically use them as electrode in a supercapacitor. So you put your electrolyte and then you just charge, and you see that it's like a square box. So it is a supercapacitor type. And then the capacitance is about 300 farad per gram, which is quite decent, I would say. So very cheap material and quite good charge capacitance in that case. So this has triggered the interest of even companies like Stora and so that are also considering not only supercapacitor but lithium ion or sodium ion batteries, where graphite is typically one of the electrodes used in those intercalated technology. So in that case, they would, instead of using polyacrylonitrile, that is typically the synthetic polymer that is used to form graphite, we can use lignin to form hard carbon. So hard carbon is not going to be as composed of nice graphitic plane of high electrical conductivity. No, it's not going to be that nice. However, it's super cheap and it can be decently good as an electrode in lithium and sodium ion batteries. So in that case, you form particles, and those particles have basically graphitic plane that are formed, but it's not a perfect single crystal, far away from that, but you have small graphitic nanodomains as well as some other voids, basically. So it's not as clean material as a good graphite, but it is good enough. It conducts electricity, and you can store a lot of energy with ions into that. So this is basically using lignin and making carbon out of lignin, basically, which is nice, but it would be nice also to use really the intrinsic chemistry of lignin. And this is what I'm going to tell you now. So using really lignin electrode and keep lignin, the nice chemistry from the nature, to try to actually store charge by using these quinone groups. So what I told you about is that the lignin is an insulator. So this is the lignin is depicted as like the network of blue things here, and each of those bonds are actually a quinone and hydroquinone groups that can be store 2 electrons, basically, and as need to exchange with the electrolyte, in that case protons. So since it's an insulator, you would need to bring a nanoconductor so that electricity can be brought there at each side. And then they must be very small then. So I depict these nanoconductors as the red solids here. So the red solids are going to conduct electricity. So the electron can come from the electrode and reach those sides here. From the electrolyte, you will have a proton that can also travel through the material and reach the same side. If it occurs, then you can have this redox reaction in the quinone, and you have this you have the ability to store 2 electrons per ring, basically, which is quite a decent energy storage material. So the trick is what are we going to use? The first findings was actually done in Linköping by Ulenganes in 2012, where he used conducting polymers, those molecular wires, basically, to combine that with lignosulfonate. And in that case, these kind of polymer were positively charged, and lignosulfonate was negatively charged. So you form like a composite during the synthesis of polymerization of polypyrrole. In presence of lignosulfonate, you form spontaneously a nano-composite of very interesting properties. So if you look at the graph there, the cyclic voltammogram, you see current versus voltage. If you start at 0 volt and you start to charge, what you're going to do is that you're going to charge your polypyrrole nanowires. So you're going to make them conductors and carrying charge. This is where you go there. Then after a while, they become very well conducting, and actually after the electric potential of these electrons is going to reach the electronic level of the quinone in lignin, and then you have basically the electrons are going to go from these molecular wires into and jump on the quinone hydroquinone groups here, and there you get the Faradic reaction, the electrochemical reaction, the transformation of hydroquinone into quinone by this electron transfer. And this is basically the red peaks that you have. It's a Faradic peak. So you see that you have a capacitive behavior due to the conducting polymer, but you have also a Faradic behavior due to the quinone that is in your lignin. And this is basically enabling a higher charge storage. So that is another example that I will skip. What we can look at is also what to do with the carbon. I mean, you can buy very cheap carbon, like carbon blacks. And then if you just use carbon black and lignin and try to mix them together, you're not going to have any great material, because there are a lot of part of lignin that are not close enough to the conductor to basically undergo an electron transfer. So that is going to be basically dead volume for the storage of electricity. And it's only at the very close vicinity where the electron can tunnel by tunnel effect on the lignin, which is an insulator, that you can have charge storage. So the storage should not be great. So if you want to improve that, you need to break those carbon black apart into small particles to get small particles and better coverage of your lignin. And this is what we have been doing. For instance, here in materials, you see this is a manual mixing. It's a SEM image where you see two types of phase, a bit a light color with a large particle, which is lignin, and then you have a darker color with a very, very small nanoparticles, which are the carbon. So by just manual mixing, it's extremely difficult to get a good material. And then you have still the two phases. You're in the you are not mixing intimately those material good enough. So the result is the following: is the black curve in the cyclic voltammogram. You see you have a capacitive behavior due to the carbon, and then you have the peak due to the lignin here. Now the peak is not great enough, so if you instead use a ball milling machine and really mash and crush those carbon black in tiny particles, and after you look at the SEM, you cannot recognize, basically, even when you do atomic elemental analysis, you cannot see any phase of any specific carbon or lignin. Everything is mixed at a very, very tiny scale, basically in a nanoscale. So it means that you succeed to bring your carbon in the nano dimension in the lignin. And then what you obtain is a much larger contribution for the lignin, because there are more lignin accessible now with those tiny conductors that you have formed mechanically. The capacity or the storage capacity is also more than double increase in that way. So this kind of very cheap material has been used by the startup Lignin Energy in Norrköping, and they've formed many kilograms of that and basically print or code by a roll fashion these kind of lignin electrodes. So recently they've obtained 30 meters of this as a test run. So, and they are working quite well, so they're very reliable. So this is an interesting track that needs to be improved still. So now I'm going to speak a few minutes about liquid state energy storage. And these are other type of battery that are now really scrutinized, and a lot of effort to bring them on the market. They're already on the market, and this is really moving forward that technology very fast now. So these are very interesting devices where basically the energy storage material is a liquid, where the element in which you store, these are redox active molecules or ions that are basically soluble in a liquid. So in that case, you have two different types of liquids, one on one side and the other on the other side. You bring them by pumps into a cell, a stack, an electrochemical cell, where you have a membrane. The membrane is very important because it keeps away one electrolyte with the others, both of them as redox active molecule. So if you don't have the membrane, you will just have spontaneous electrochemistry, and then you will just produce heat, but you're not going to produce electricity. So if you want to produce electricity, you need to separate them and keep them away, and then this membrane will be basically crossed by ions, protons in that case. So you will have one electron exchange at one electrode for vanadium, for instance, 2+ to 3+, capturing yes, and then you will have on the other side the vanadium VO2+ and VO2+, the other one, that are going to react here, and then the protons need to cross the membranes, and the membrane should keep as much as possible the four different type of reactant separated, which is one of the failure in these kind of specific batteries. So one of the things that is important is to have a very, very porous electrode, to have a lot of surface exchange between the electrodes and the liquid. So the more nanoporosity you can bring to your electrode, the better it is. And this has been one of the strategy. Instead of using common carbon fiber that are 10 micron in diameter, it has been to use lignin and to do electrospinning of lignin to get nanofibers, and then carbonization to get basically a carbon conductor at the nano dimension. So lignin has been used to form nanofiber by electrospinning followed by carbonization, reaching a very much higher surface area, and this means basically higher power for your battery. So the next thing that lignin has been used to is actually to combine that with Nafion. Nafion is a membrane that has been used because of its chemical stability in these vanadium redox flow battery that in a very strong acid, basically. The problem of Nafion is that this is not very good for this kind of ion, because the ions are crossing the Nafion quite a lot, and this is a problem for the battery. So what people have done is to combine Nafion with lignin to actually prevent those vanadium ions to cross the membrane, but still allow the protons to cross to do the electrochemical reaction at the electrode. And this has been working quite well. You can see here on the curve, the first one is a discharge curve, so meaning that the introduction on lignin in the Nafion membrane didn't change the energy storage ability, no, but the retention and the ability to store the charge and to keep the charge stored has been improved a lot. This is what is called the self-discharge. So when you charge your battery and you don't do anything and you look at the open circuit voltage, how much the voltage is spontaneously decreasing. Here, if you don't have lignin, you see that within 10 hours, the potential drops significantly because all the ions are just crossing the Nafion membrane. But with the lignin coatings on top of that, you basically have a much longer self-discharge. You see, you get 90 hours. So it's a much more improvement. Then finally, another exploration track is to use lignosulfonate as the reactant in your redox flow battery. So using the highly concentrated lignosulfonate as one of the reaction here by the same quinone chemistry that we are using, and use another kind of reactant such as bromine, another redox couple. So those battery works are not the best one, but still it's very cool to see this kind of effort to use lignin in batteries. So in conclusion, lignin can be used as a precursor for carbon electrode, as a membrane separator, and then if you want to composite that with a nanoconductor, such as conducting polymer or nanocarbon, you can use really, you can obtain a nano-composite for charge storage that is very cheap. So needs to improve lignin is increasing the phenolic content, as well as increasing the solubility for the liquid state batteries, basically. So I thank a lot of co-workers, the Laboratory of Organic Electronics, and I thank you for your attention.
Oh, thank you very much, Xavier, for your wonderful talk. Takes us through the fundamentals of energy storage, and then connecting that to lignin. I think it was a very beautiful presentation to some of us who are especially not in the electrochemistry branch.
Yeah, that is really the goal of this talk, is to basically bring what we are doing there, and we are really lacking the chemistry of lignin. So we really need to find now new, more advanced ways to increase energy density, solubility, etc., and both in the same time. So there are a lot of interesting things to be done on that area.
I totally agree. Very good. Now, we have some questions here from the chat, and I advise participants to continue with their questions. We have one from Amiresa, who says, isn't it that the aromatic rings are broken after carbonization at high temperature?
Yeah. I mean, the aromatic rings, after carbonization, they become like graphite-like, so graphene-like. So they become conductors, but they lose then their ability to store charge. They are just becoming conductors. But they are used then as intercalation material. So the lignin chemistry is not used anymore like this quinone redox ability. Then we are then using more the conducting aspect of the carbon that you create, and this carbon can intercalate ions and have another type of charge storage.
Very good. And while we wait for some more questions, I have a few here. Maybe I'll start with one. It was very interesting that you mentioned the use of lignosulfonates, and that is partly based on the charges, the negative charge on the lignosulfonate. My question is, can this be substituted by some other negative charge, such as a lignin that has carboxylic acid groups? Would that suffice for this purpose?
Yeah, yes, certainly. Everything is a question of the pH at which you are going to do the polymerization. But I guess yes, and I have not shown that. I can just show you that slide just to illustrate one simple experiment that can be done. For instance, in that case, what we did is we synthesized a nanoparticle as well as a film of PEDOT tosylate. So PEDOT is a conducting polymer that is positively charged, and then the tosylate is a sulfonated small molecule that is then negatively charged, and it is compensating that. Yeah. So when you have this film and we dip that in a solution of lignosulfonate, what we observe is that the lignosulfonate is actually going not only on the surface of the material, but really inside. So it means that these polymers, they are easily swelling by the solvent, and that is enough for the even lignosulfonate to come and go inside the material and completely change the material on something like 100 nanometer thickness. So we could form we could form like this first nanoparticle of P-dot tosylate. We dip it in lignosulfonate and completely ion exchange, and we get a material for battery in a very simple way. So if you do that with a lignin with carboxylic acid, it would be, of course, very interesting. Just tuning the pH, and you will be able to do that. I guess it would be interesting.
Okay, very interesting. And as we wait for more questions, maybe I can continue. You had your system where you have you show very clearly that in this carbon black, there is some kind of lack of contact that might affect the efficiency of your lignin. So you perform this ball milling on your carbon material, and then you show very clearly that the efficiency is improved. Now, one problem could be related with the energy that you have to put into the ball milling. Could this be mitigated by instead using smaller lignin molecules that would have better contact with the non-milled carbon black? Do you see that as an alternative?
Yeah, I mean, definitely here is just a very, let's say, it is like is not using the smart tool of chemistry. I mean, we are just using ball milling. So, but yeah, there are very many more exciting track, I think, that could be used both on the lignin side and on the carbon side. So, for instance, I mean, nanographite can be to some extent dispersed in very strong as a basic media. Yeah. Lignin can be also dissolved in basic media. So you can probably bring them, and we have done some attempts, but we have not worked enough on to that. But this could be a way to bring them intimately together without having to use a big hammer of the ball milling. But yes, and the same. I mean, if you have a very low fraction in carbon blacks and other, you have a very large surface area. I mean, you have 1,000 square meters per gram, basically. And these are very, very tiny, small pores. But if you find ways to bring the lignin inside, that could be also interesting. The problem and the challenge is that they must kept after insoluble. So if you are in contact with an electrolyte, if you have the right electrolyte that does not dissolve it back, it's okay. But otherwise, you need to find in addition a strategy for cross-linking them or connecting them to the carbon. This is also, I guess, possible, but that would be that there is a lot of chemistry and interesting track there. Definitely, this is yes. Yeah, interesting. Yes.
Very good. Then you let me check with Josephine if there are any questions from the YouTube channel.
No, we don't have any questions from YouTube.
Okay, then I will probably continue as we wait to see some more.
We have one more question in the Q&A.
Oh, yes. Yes, sorry about that. So we have a question from Ami Reza, who says, about the cyclic voltammetry of lignin after adding nanoconductor. Have you done large window cyclic voltammetry? And then a follow-up question would be, any other oxidation or reduction peaks elsewhere than the quinone peak?
Yeah. So of course, I mean, you can probably over-oxidize the lignin and start to attack it. That is for sure. And then also what we have observed is that typically there is a part of I don't know if I think I have that. There is a kind of preparation of lignin, and that the first peak that you typically observe is there is a reaction where you basically remove the methoxic group there, so to get this kind of oxidation, which is actually very important because it enables the lignin to be prepared for storing more charge. So this is a reaction that we have not fully understood. We started some time ago about trying to understand that, but we have not reached yet any conclusion. but so after that, there will be also other peaks from lignin by attacking other groups where you can be then you can start to destroy the lignin instead. So you need to be careful about the voltage range you are working on. It's the same for conducting polymer. You can destroy them also.
Yes. And I do have a follow-up question to that. Actually, it is still connected regarding over-oxidation of your lignin. Isn't it so that if you now take these quinones and oxidize them further, what you are likely to get are muconic acids, which are still conjugated? So would that affect the storage if it is still in an aromatic system that are, open ring aromatic system? So if you have an acid which is conjugated,
yes,
penultimate carbon, would that positively or negatively affect the energy storage?
I mean, since it's not a conjugated polymer, actually, I don't know the answer. If it was a conjugated polymer, for sure you break the conjugation path, but it's not. It's just an aromatic ring. So I mean, if the electronic levels are not changed too much, and if it's a reversible reaction, maybe it is possible. Yeah. But I don't know. Yes, I don't know actually. I would say probably not, but I don't know. We need to check that.
Okay, let's see. Yes, I don't see any more questions on the chat. So just the last question out of curiosity from me would be if you had your lignin Nafion membrane system. So what source of lignin was that?
Oh, it is certainly not lignosulfonate. Lignin, otherwise it's soluble in water. Okay. But which kind exactly, I don't know. Yes.
Okay, all right.
So and that is a difference. And if you want to combine that with a conducting polymer that is typically p-doped or oxidized in its conducting state, then you use rather lignosulfonate. Okay. And then this electrostatic interaction between the lignosulfonate negatively charged and the conducting polymer positively charged actually makes it insoluble. But if you want to use carbon, then of course you cannot use lignosulfonate. It's going to dissolve directly. But then you need to use a Kraft lignin that is insoluble. And the Kraft lignin has somehow the disadvantage is to be not a good ion conductor. So to bring ions, you need to bring both electrons and ions. You need also to maybe some level of either carboxylate, as you mentioned, or sulfonate groups to actually enable the ions to move in the lignin too. So you need both. You need both the electron to reach lignin by the conductor, but lignin, if it needs also to be able to basically transport to some extent the ion that facilitate the phenomena that we have seen, because you need to have both electrons and ions moving in the material. So there is a fine tuning to be done between solubility and then the level of sulfonation, and then there are many different ways to introduce also conductivity of ions in lignin eventually that we have not explored. Making lignin an ionic conductor would be an interesting strategy also there. But we need always to try to get as much redox activity as possible. So to add on top of lignin and functionalize lignin with a dyes or catechol or different tracks are of course very interesting things that we are trying to explore at the moment, basically. But there is a lot of cool stuff to be done there.
Exactly, very interesting. It looks like the sky is the limit.
Yeah.
New area. So with that, Xavier, I would like to thank you very much for agreeing to participate in this seminar series. We surely have learned a lot here, and we'll be following the developments in this interesting area of lignin in electrochemistry.
Thank you, Martin. Thank you a lot.
You're welcome. So with that, I hand over to Josephine for some final comments.
Yeah, nice to you. Thank you very much for today's talk. It was really interesting, and it's interesting to see how much use you can have of lignin in different ways. We will be back now on Thursday, and then we will have Martin, Professor Martin Lavoko presenting. Yeah, now I remove the spotlight for you too. So I hope that you will join us then. It's Thursday, June 10. And finally, thank you for you who've been following this webinar. So
Thank you.
see you on
See you.
Thursday.
See you on Thursday. Bye-bye.